Hello, 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 Sarah. Hello, Amber. Hello, Wen Yi. Hello, Shirin. Hello, Aishan. Hello, Justin. Hello, Aaron. Hello, Kimberly. Hello, Armand. Hello, Wen Yi. Hello, Eileen. Hello, Jenna. Hello, Kermit. I mean, hello, um, Yaobo, whose name I would say wrong.
Hello.
Hello,
You
um,
see it right?
I do. Okay. All right. Thank you. Okay. Good. Hello, Andre. Hello, Alinelli. Alanel, I'm still. Hello, Armand. Hello. I know this is all awkward. I'm trying to make it less awkward. Hello, Eileen. Hello, I think that's everybody I see so far. I totally appreciate as usual. Oh no, there's not. Oh, hello, Aaliyah. Hello, Andre. I said Rachel. Hello. Oh, I did. Oh, I did really. Okay, great, cool, awesome. I won't try twice, but great. Oh, and Alyssa's here. Okay. I think that's just my. If I didn't say your name, I do apologize. Hello and hello, Eileen. All right, cool, cool. I This is so weird. It's been and good afternoon, yes, and hello. Okay, cool, cool. So I feel like it's been forever since I've seen you. It has been. It's been so long that that strangely, as you can see, I missed you so much. I even tried to grade your papers. I think I think it's fair to say that everything you've anything that you've turned in, I think, I hope, as of this moment, you've gotten back. I mean, unless you just turned in something like in the last couple of hours, which is fine. If you did, nothing is late on your, basically nothing. You guys are not late at all, is what I'm trying to say. um and we're ready to start really pressing on with the material. I'm hopefully each day is getting clearer to everybody how we're doing this class. um Again, the participation, I think, is really working. I really appreciate the fact that people have mute off unless there's feedback in it. I appreciate the judgment all of you are using about your videos and everything. So we'll just keep going with that. Um, I don't even think I have any items of business for you. If you don't, for me. Oh, sorry, the board is weird. Um,
Professor, I have a quick
yeah,
question about
yeah.
the assignment that we did
Oh,
in.
yeah.
So you told us before that we didn't need to do the vectors part of the problem, but then you put in like the comments with the grades that we would get full credit once we submitted in the vectors part. So I was just wondering, is that because we're gonna like cover it more and we're supposed to resubmit it afterwards, or like what's the
Right.
deal
Okay.
with that?
All fair. All very fair. No, totally fair. Yes, I knew there was an item of it. That is a good item of business. Right. Okay. So first of all, let me start. Yes, there was some. I created some confusion there, and I apologize. And partly it's because I sent slightly different messages to the two different sections, and I'm getting them slightly confused. But it's absolutely true. While I was saying, don't worry about the math part. I mean, the vector part of that sheet. Wait, let me back up to everybody. Again, absolutely fair question, and we're talking about the homework number 2 math methods sheet, which at this point tons of people have turned in and gotten back. But just by the way, like sidebar, if you haven't turned it in at all yet, it's still fine. We haven't started going over it at all. So anybody, so please do take a look at it if you haven't turned it in yet at all. That's fine. But then it's true. For a while, I was saying, don't worry about the vector part of this. And then I think I thought I had at some point, once I made it June this week, I gave myself the perhaps misimpression that then I had realized I put instructions in the sheet that could help you try it anyway. So I thought I had in fact said go ahead and do it. But I realized I sent mixed messages about that. The main thing I want to say to everybody is like, if you already turned in a bunch of the sheet and because I what I'm saying is it's not a punishment at all and nobody's late. I totally did say hold off on the vectors. And we're going to start going over that whole sheet today. But I think now, I guess I'm officially saying, to be as clear as possible, I think because there's instructions in the sheet, I would like people to try those vectors, even if it's, before we get to going it over in class, because that sort of is the way of physics. And I'm now officially saying, please try the vectors. But even more importantly, what I'm saying is, like, anybody who already handed in the homework and got tons of points, and I already, saw it, and the other professor saw it, I'm just saying now, if you, yes, I'm saying it's not a punishment or your mistake. You didn't owe me anything. You're not late. But since it's all just part of one assignment and I don't have a different portal, if and when any of you then finish trying the vector part, please just add that in and I will totally change the grade to a 50. The one thing I've now tested, so I know that it sounds like I'm skirting a line there. I'm not saying that anybody who turned in the sheet but didn't turn in the vectors did anything wrong. In fact, basically what I'm really saying is anybody who did that sheet, especially if you did it early enough when I hadn't said anything about the vectors, is totally great. But yes, I think we're now at the point where everybody could try to turn in the vector thing and then get the full 50 points for the whole sheet. What I've now tested fully and proved to myself, I'm not sure if I believed the following last semester. I'm not sure if it was true last semester, but it's definitely true that for any one of you, if you do a homework and you get a grade on it, like whether from me or from Professor Lou, but like most likely probably me, if you get a grade on homework, it absolutely turns out that you can submit more to that same portal. As long as I don't take the portal down, you can add more to that, even leaving your old document there, which I would prefer, but you can add more to that. And I will automatically see that you did. Like, I didn't believe this before. And again, it might not have been true before, but if you add something to assignment, even if it already has a grade on it, automatically that will bump to my side and like tell me to grade it. And even though I'll see a number there, but I will see that there's something going on that I need to look at again. And then I'll open up the new document and I will absolutely change your grade. And it's not, and this part, I'm actually really happy about this. This is to everybody. This is all part of I want people to feel like anytime they're doing more physics or better physics or adding to physics, that you just get that many more points for that. This is net. So in other words, if you ever get a 47 out of 50, it just means there's 3 points left over you can still get. And you will know, any one of you will know very explicitly, like I will explicitly make it clear, if I'm actually ever taking off points for being late on something, like it will almost never get to that point. That would be only relevant like on exam situations and honor code and things like that. But with these homeworks, so if I ever say for full 50 points, please submit with blah, blah, it is not me telling you that you did something wrong or you didn't hear the instructions right, or nor am I trying to like change the instructions. I'm just saying, here's what's left for the full 50 points on that. And whenever you do it, great. This is to everybody. It's actually the reason that to be honest, really honest to everybody, I actually feel much more empowered and motivated and invested in grading all your stuff, like much better than I did last semester, which was horribly and not at all. It's actually much easier for me to do it now with this mindset of knowing that everything is improvable, that I can give numbers much more quickly and happily and feedback much more easily if I don't think that every time I'm giving you guys a number, it's dealing you a death blow. Really, like the Google Classroom thing is like sort of opened up a chakra for me. So please, all of you understand that at any moment, if something is like worth 50 points, it's just at any moment, hopefully I'm just giving you a clear path of how you can get those 50 points and then you just get them and then that's it. So today we're going to go over stuff, but I'm not going to give away. We won't even get to the vector things today. So anybody who goes back in and he still hands in the vector thing to me, I'll still know that you did it even without my instruction, and it'll be all the more impressive. And that's the, okay, sorry. Oh, God. Yes, I see people in the waiting room. I'm sorry, I get so caught up. Yikes. Sorry. Right. All right. Waiting room coming. I'll pause for a second. I'm looking in the chat. It's so carried away. That's not the chat. That's the cheat. Wait. Sorry, how long did I keep Abby waiting? I'm sorry. Okay. Okay, but it makes sense. Okay. Hopefully that all of what I just said makes sense. Look, really, this is a secret way of saying too, I'm trying to give a lot more feedback and quicker and more frequent of it to you guys. That I think it was terrible how little I gave last semester. I don't want to talk about it right now, but it's true. And it's not like anybody else complained to me. You guys were very like generous about it, but it's not the way I want to repeat this semester. And what I'm learning with all of you is that the more frequently we can interchange little things rather than, big things sporadically, like the better. So yeah. So on the homework, what we're on to now is, what's due these days, what was just due is mathematical methods, but we're still not up to going over it in class. So anything any of you does on mathematical methods from here on is worth the full 50 points, is worth full credit and my feedback. And if you've already done and gotten it back, great. It's also understood that you're that on top of the class. Like that's just the way. But I think we're still in the middle of sheet one, or the end of sheet one. Like I think, take a breath again in a second, but. Okay, now, so I'm just let me look in the chat, but this is where I think we actually are in the class. Like I'm trying to shift gears back to where I think we are talking in the class. Like we've done a lot of work on this one sheet. I know all this energy talk and everything, but I believe, and I'm checking the chat in a second, but I believe we're up to the last question, which is like really the point of the whole sheet. The last question is what gets us into the new math and the new physics of this class. That's where I think we are. And I think the last question is at 1 second of this motion that we've now started to describe as harmonic oscillation. We just started to describe it that way, but it doesn't say much. But we're asking at 1 second into this motion, where would we expect to find the mass? That's what I believe we're up to. But first, let me check the chat and make sure I'm not crazy, but I am crazy. Oh, cool. Thank you. Oh, yes. Oh, and okay, wait. Sorry. So thank you for the chat. So number one, someone's saying in the chat that we are question 9. Good. All right, that's what I'm going to do. But also, I'm getting a question in the chat, which is very fair and reminds me. Okay. Because you guys are being good about the homework and because I'm trying to go through it a little bit more thoroughly, right, a couple of things. One, definitely to any of you, and I don't mean this is, if any of you gets like a 47 or a 48 or something like that, I mean, the idea is that I'm not trying to be picky about wrong answers. So if you got a 48 or 47, it's almost undoubtedly a picky formatting request on my part that I have, that if you can just correct the formatting thing, then I would give you back the full 50 points. And it's and so for example, it's true in a lot of the cases. I'm saying to people, wait, let me back up to everybody. So especially if we're trying to get better at homework and in just like research habits in general, like a big thing with everybody is please circle the answers. I know I said it last time, but just the harder the homework gets, bear in mind, the more tempting it is to not circle your answer, because really the harder the homework gets, the more tempting it is to not really actually get to a final answer or to not feel confident about it. So please circle your answers. But then another thing, so maybe soon we might be getting to the point where I'm giving someone a 48 or 47 just to tell them to circle their answers. And then all they have to do is then like go take their homework, circle them, put it back in, and I'll give them a 50. Again, it's just meant as a communication thing, not as a punitive thing. But the other reason I might have given someone a 47 or a 48, and for example, there's a couple questions about this in the chat, is this formatting request I have about putting things on a separate sheet of paper. I used to make a big deal about a PDF. I realize now the PDF thing turned out to be unnecessary because of technology now, so great. But I do make this point of, I give you questions, I give you guys a problem sheet with like a thing on a spring on it, and then I'm asking you to turn in your work on separate blank sheets of paper. That's an old teacher habit of mine that I ask for that. And I always ask people not to write their answers on the question sheets. But let me actually take a moment to explain that, because actually the rule does need to evolve, I'm beginning to see. But let me explain where the rule comes from, like why, especially when we're actually doing homework and I'm grading it. The old purpose of that rule, why, and again, if that's what I'm saying here to any of you, if I give you a 48 because you did your homework like on the homework sheet itself, and I'm saying please do it on a separate, we can make a compromise that I'm about to tell you, but there's a reason for why I do that. The reason that I tell people not to do their work on the problem sheet is that invariably the problem sheet does not give you enough room to do proper solutions, to either think about them properly or to make them readable, to make them legible. Now, one could argue, well, then Yaverbaum, why don't you freaking give us enough room? And that's and that is a good thing to raise. Like, why don't I? And I used to do that on exams. Exams used to be that there was a question, then you had a whole bunch of space to write in all your work. And then the next question, then a whole bunch of space. I did used to do that. And it's right. I'm not trying to turn the burden on you guys, but here's the problem with that I've run into. If I give you, quote, a whole bunch of space after each question, unless I literally give you a whole page for each question, no matter how much space I give you, I'm still giving you finite space. I'm still asking for you to think about your answers in my little space blocks. And then especially if it's a long document or something, if I start giving you more space for one block and less space for another, it starts telling you how to expect how I'm thinking about the problem, and starts telling you to start fitting your thoughts into my space, which is actually really bad for your thinking. And I mean this honestly to everybody. So for and it was really bad for me when I was a physics student. Like, what you really want when you want to think about physics is you want to, and this actually I learned from somebody in the class too, someone who last semester made a suggestion about like making your own actual workspace in your apartment that's a dedicated workspace, and make a different, like, that's a really profound advice during, COVID and everything. And it actually applies to the piece of paper itself, that you guys, when you're actually sitting down to solve a physics problem, you don't want to cram your thoughts into a limited period of time or a limited period of space. You want to feel as though you have the expanse to work with, which is why I advocate blank paper. And always have advocated blank paper. It makes all the difference in the world. In fact, for a lot of people, I would say, by the way, get rid of the graph paper and get rid of lined paper. Like, literally try blank, at least try it. However, I know I'm talking about this a lot because now that I really do want to take your work seriously, I did notice I'm trying to be a student too and do my own homework on Google Classroom, like you guys are, to see how this actually feels and like what this is actually like. And I realize that for many of you, if you're doing homework on the computer or on a tablet or something, if trying to make homework as easy as possible on you, I realize that if you have to do the homework on a separate sheet, that does possibly create a whole new level of attachment nightmare that adds much. And then you have to keep flipping back between the questions and the answers, which is a complete hassle. I actually do see that. And I keep trying to work on my own solution because I don't think you should be putting your answers on my question sheets. It's not that I care about the question sheets. It's not like you can't have them or deface them, but it's just that I don't want you thinking about things that way. So here's a compromise to everybody. It's the first time I've said this, because I realize having the questions right in front of you while you work, it makes it much easier. And especially if you're working on a tablet with a stylus or something, which probably is the best thing to do, and you're trying to do your homework straight into Google Classroom with a minimum of hassle, I totally respect that you want the questions right there, and it's easiest to work on them right there. So here's my suggestion to everybody. Again, I don't want to overcomplicate this. I could put this in an instruction manual or something, but one thing I've noticed, what you could do is take my document and just add a bunch of blank sheets to it. Like, take the first page of my document and then add a blank sheet right after and start doing your work on the blank sheet, and then more blank sheets as you need them. So you can have the questions right there in the document, but just don't try to work right there. Like, or, some of you are really fancy schmancy. If you could take my PDFs and like, chop and paste them or whatever, or take screenshots a little part, if you want to get fancy, go fancy. But I'm saying to everybody, I realize we don't need to get fancy here. And I realize you need the questions in front of you while you're working on the answers. I do see that. And I mean, I need it too if I'm a student. But please, everybody, what I'm trying to say is don't try to fit your work into finite spaces. It won't work, and I won't be able to read it half the time. So if there's nothing you can, so if anybody got a 47 or a 48 or whatever, and I'm not trying to spend the whole class on it, it's an issue like that. But honestly, at this point too, having said all this, if you had a 47, 48 and there's nothing you can do about it, or you could only do something about it going forward, you could just write me a note and say, I get it. I heard your thing in class, and I'll change your score to a 50, like anybody and everybody, like, because it's really not meant to be like that type of thing. But yeah, we all just want to make homework doing and homework grading, as we just want to reduce all of the hassles just to physics thoughts and nothing else for both of us. So that's that. I hope that helps at all. Right. Oh, and fair question. Okay, so Sarah's singing it. Right. If you write on separate paper, you do not have to. There's a fine art here and a fine line, but again, I've been practicing it myself to see what works. If you're doing it on a separate piece of paper, you do not have to copy down the full question. No, but just label them kind of like, and this is what I'm trying to do on my board here to shift everybody back to this. Like what I'm sort of trying to do for you guys when I work on the board in class is kind of model what the solution would look like that I'm looking for. And honestly, I don't have the sheet in front of me when I'm doing this class. Like that's too hard of a hassle for me to flip back and forth. So here's my best version is I'm just writing like question 9, assume t equals 1, x equals, like that's good enough for me to know that is the question, right? I didn't copy down all the words of the question. I didn't cut and paste it or whatever, but it is clear, like that's what I'm about to solve for. That's ideally what I'd like from everybody, like just enough to make clear what's going on so that I can look at this without having to go back and forth any more than you. I don't want you to have to go back and forth or me. So just enough to keep it. That's the best I could say for, but we're all working on this together. It's all work in progress. And I promise, honestly, I mean, you know, if you guys, anybody who's doing the homework every time, and especially getting it back, if we're down to this level of concern, you know, then you have nothing to be panicked about. It's just to make the whole system go better. But all right, so this is where we are. We're assuming t equals 1. We're asking for what's x when t equals 1. Now, this problem is asking for a numerical answer. And there's a way to get it, especially there's a way to get it to like get on the web and find a procedure. But I actually really want to understand this now. We're about to get into physics here because as many of you made clear to me in the homework, like we're asking the simplest, most straightforward, most central physics question there ever is, which is at a certain time, where's something going to be? Like there's nothing more straightforward than asking that in physics, but there's different kinds of conditions for that question. And we spent a long time in the beginning of physics 1 learning a whole bunch of conditions where our answer in physics 1 might be something like, oh, you know t and you're looking for x. Why don't you, Yaverbaum, do something like x equals 1 half a t squared plus v naught t? Like you have t, you're looking for x, do one of your old xt equations. That, yes, when they work, and that's what we do. But like many of you already pointed out in the homework, and I know you know, that won't work here because even though this seems like a simple, repetitive, patterned situation, all the simplicity and the pattern and the symmetry of this situation that we spent the first 8 questions investigating, all of them show that one thing isn't constant, and that's acceleration. The acceleration is not constant. So all of our constant acceleration equations from physics 1 go out the window. Like they're still like right, but they don't apply here. So we can't use constant acceleration to get our x as a function of t, but also then all the energy methods we used for the next, like we used acceleration methods for the first 3 questions on the sheet, acceleration and force. Then for questions 4, 5, 6, 7, we realized, oh, acceleration isn't going to work for us. So let's talk about energy now. So we used the conservation of energy to get all these other answers. But now here in question 9, the simplest question of all, at t equals 1, what's x? Even energy won't do anything for us because energy is all a speed distance trade-off or a position speed function. Energy, remember we were saying over and over, is homogeneous in time. I mean, systems that conserve energy are homogeneous in time. They're symmetric in time. We don't have any functions of time that yield position from either the energy method or the acceleration method here. So it's a very simple question that is going to force us to look at more complex methods of answering. The one thing I want to make clear before I go any further is technically the question is when t is 1, what's x? But really, as a physicist, to me, the question is, given t, what is x, right? Like I don't care, t being 1 second is just a particular example for this particular question. The real issue is if I know t, can I get x? So what I'm really looking for, what we seek, we are looking for x as a function of t, that, right? We're looking for some function that maps x to t such that once I plug in some value for t, like 1, it will spit out an answer for x. But again, I want to get an answer that'll work for all time. I don't care only for 1 second. I care for any t. So we're looking for sorry. Okay, we're seeking x equals t. Okay, and just as a like a side note reminder, that's almost always what we're doing in physics. That's what we spent most of our time in half of physics 1 was seeking what x is as a function of t. We eventually got it. We got a function like x equals 1 f a t squared plus b naught t. But every new physics situation is a new set of conditions under which we seek that. Now, this condition, the first thing we know about this condition is a is not a constant. A, like that, one thing we know is that we cannot rely on the constancy of a here. Well, what can we rely on? Well, one thing we know is that this is a spring. We know Hooke's law. Like we know that Newton's second law is always true. Sometimes it's always true. The sum of the forces on an object at any moment will equal the acceleration of that object. And we know that the one and only force that's acting here right? We know how forces work in general. They produce accelerations. We know there's only one force acting here. It's the spring force. So we know here like really the given of this situation, all that's been given is that a spring is acting on a mass. So all that's given really is negative kx equals ma, like the free body diagram is given. That's what's given. And we're looking we want x as a function of t, right? And there doesn't seem to be any t in what we have given. There only seems to be an a, but there is a relationship between acceleration and time. And if we're very specific, right? I mean, we know that average acceleration is change in velocity per time. Like average acceleration is change in instantaneous velocity per time. But instantaneous acceleration is the instantaneous rate of change of velocity with respect to time. And velocity, instantaneous velocity, is the instantaneous rate of change of position with respect to time. In other words, by definition, I guess I said this last time, and I know a lot of you, but oh wait, like what I'm saying right now is so like this is how I would approach this problem. Like question 9, like I have to write down what I know, and try to relate it to what I'm looking for. I'm looking for x as a function of t. I know that negative kx equals ma. If nothing else, even if I don't want to be clever or sophisticated, what I'm looking for in my mind is some relation between a and t, so that I can get rid of the a and put t in there. Because I'm trying to get x and t related. Well, I know velocity is the derivative of position with respect to time. I don't know why I'm doing this all in blue. Like that's its definition from calculus, right? This is what I'm saying so far. And this is about as far as I got in anybody who did the homework who, and this is still homework 1. Now we're talking, right? Like, and still, again, if you haven't done homework 2, just do it. I mean, we haven't said anything about it yet. But this is homework 1 and some people totally got, and I'm very aware, a lot of you like actually did a bunch of things that I'm about to do and got an answer. And some of you understand what you did it or made it up in your head. Some of you didn't know how to do it, but got it from the web or a book. But then once you got it and you wrote it down, you understand what you wrote, both of which are cool. Some of you got stuff from the web, wrote it down, and know in your hearts that you don't really understand what you wrote down. I'm not here to chastise any one of you, but I'm here to say that definitely if you know in your heart that you wrote a bunch of stuff that you didn't understand, then this is the time to so bear with me and you'll find out now what it is that you wrote down. But it does take some thought. But this far, as far as I got, this is about as far as I would get writing on anybody's homework. Like if they wrote, I have no idea, or here's where I get stuck. And hopefully more and more people don't just write, I have no idea. Hopefully you write something. But a lot of people started it and said something and then were like, I don't know what to do from here. This much is what I would advise. This much, if you think about it, hopefully makes sense. You might not have thought it, but it's all about when you don't know what to do, churn definitions at first. Always go to definitions first. So that's what I'm doing. So I have this now. Now we're almost at something here. We really are at something now. Because remember, my goal is not numbers. At the last minute, when I have a number, my goal is functions. My goal is to get X on one side and a bunch of stuff on the other, a bunch of letters that are all constants and a T on the other. That's my goal. And I'm getting there because now I at least have an expression that only has X's and T's in it. And I'd be careful. What do I mean? I mean, like this expression, like I'm saying, I'm getting somewhere now. If I look at this last line, like nothing, maybe what I've done is stuff that people might not have thought of, maybe, but nothing I've done is made up, right? Like we didn't make up any new information or like pull any fast moves. We're just taking information that we do have and putting it together. But now we have this statement here. We have this statement here that has no numbers in it at all, just a bunch of letters. So it can look like a bunch of gobbledygook. But there's a difference in the way that these different letters are functioning. Like M and K are letters, but they're constants, meaning they really might as well be numbers. In fact, you know that like M basically really just stands for 0.3 kilograms and K stands for 200 newtons per meter. It is a number. We're just not writing it as a number because we want to acknowledge that like even if we changed K to 300, this whole relationship would still hold. So K and M are just numbers. They're not variables. They're letters, but they stand for constant numbers. It's the X and the T that are the only things left in this expression that are variables. And that's as it should be. That's what we want. That there's only 2 variables in this expression. And in fact, specifically, let's make this totally clear. And I am using X rigorously. That is, it is the same X on both sides. I can't divide both sides by X. We'll talk about it in a minute, but they do, both X's refer to that same position variable measured in meters. And that variable is the dependent variable as opposed to time, which is the independent variable. Now, how do I know that? Just from the way this thing is written down, since like X is on both sides, I know that this expression is treating X as the dependent variable and treating T as the independent variable, not because there's a rule in the sky, like sometimes T could be something else and sometimes X could be something else. But here, T is being treated as an independent variable, I know simply because it's in the denominator of a derivative. Like just that notation, whenever you write, like if you just look at the notation of how we write derivatives, it's always the derivative of something with respect to something else. The thing on the top is the dependent and the thing on the bottom is the independent. And I'm saying all that because that's good news, because that's what we're looking for. That has the right form. Like remember, we want X to be a dependent variable, which depends on the independent variable called T. So like we're getting in good shape here that we have this expression. It's getting us somewhere, but we're not there yet. This expression is now where things get maybe both clarifying and intimidating. This expression here, as much as it has the right contents, the contents are arranged in a very locked down sort of way. Like this expression is not telling me a rule such that if you plug in T, I get back out X. That's what I want, but that's not what this is giving me. This is giving me a rule that says something about the rate of change of the dependent variable with respect to the independent variable. It doesn't tell me about the dependent variable. It tells me about the rate of change of it. That's a little bit annoying, first of all. Second of all, it's thick enough, like these are really derivatives that like I definitely cannot divide both sides by X or something like that. The best thing I can do to clean this up, just to repeat, so
Professor, there's still someone in the waiting room.
sorry. Oh, thank you. Wait, really? Because, wait, that's too bad because, wait. Oh, yeah, you're totally right. There totally is. And I am totally, oh, sorry. Okay, sorry, thank you. Right, okay. You know what's, I shouldn't say this. I might say it later. All right. Thank you. We have. Sorry. This is not math telling us this. This is physics telling us that this is a situation. Now I'm going to clean it up a little bit just to. We can't divide both sides by X. It's not that kind of equation. But we can clean it up a little bit so we can start staring at it. So I'm going to divide both sides by K, just to collect. Hang on a second. Okay. Hello. Hi. How are you? This is class. That's good. This is class.
When are you going to be done?
That's what they're asking also. I'm going to be gone in 35 minutes, a little bit less.
Too long.
Yes, that's true.
Be done in about 10 minutes.
I will try, but I have to
That's
actually.
long enough.
I hear you, but I have to actually do it in order to be done. But right after, are we doing? Right after we're doing Sword or Minecraft? And then
Minecraft.
Okay, excellent. It's a date, and I've got to do. Do you want to say hello? If you're not going to say goodbye, at least say hello. Okay, I've got to teach now. Thank you. Thank you. You can have those too. Thank you. Okay. So that was him and this. Oh, that's very nice. Oh, wait. Oh, no problem. Oh, that's very nice of you. Thank you. Wait, someone else is here too. One second. Yeah, and this whole thing, like, so this is his vacation, is sitting at home while his mom and dad work from their bed. It's just ridiculous. Like, I don't want to be you guys during the quarantine. I don't want to be me, and I definitely do not want to be a kindergartner during the quarantine. It's horribly unhealthy. But we are, as you know, going for that Nintendo scholarship. Oh, and if anybody, wait, what do you want me to ask you actually? If anybody has any tips, what is he? He's looking to trade. He's looking to trade. He has like a level 95 Moltres that he's looking to trade for a level 94 Mewtwo or something like that in in Let's Go, but we could talk afterwards if anybody's interested. Okay, but anyway, what I'm saying here, I haven't answered anything. I haven't solved anything. I'm just rearranging this equation now to make it look a little bit more dealable. So I just collected all the, this is what physicists do. We collect all the constants, put the constants together so we can treat them as one set of numbers or even just one number. And then we separate the variables as nicely as we can. So we have what we have here, this thing in blue at the bottom, which I'm going to recopy on the next page. It's worth staring at for a minute because all it is in a way, oh, sorry. Oh, okay. All right. All we have here in a way is just a translation or like a rearrangement of Hooke's law. This really is just saying Hooke's law applies. It's really just saying we have a situation here with a spring and Newton's second law applies because it always does. So it's really just saying Hooke's law, but it's saying it in a way that shows how the variables are related. More specifically, it's saying it in a way that relates a derivative of the dependent variable to the dependent variable itself. This has a special mathematical form. This is called a differential equation. It doesn't mean we've solved it. It means we have to solve it. But what we've just stumbled on in physics, like by doing the physics, we as students in this class, or like if this were the moment in history, like when Hooke works us through and Newton works us through, we find ourselves in history like, oh, on this new mathematical entity called a differential equation. If we are to understand the physics, we're going to have to unpack this mathematical entity. Now, you have not taken a class in differential equations, or I didn't ask you to. I don't want you to have taken a class in how to unpack these mathematical beasts any more than Newton or Hooke took a differential calculus class. To like, they had to figure out a way that made sense. And that's what we're going to do. We're going to figure out how to deal with a thing like this, and then we'll call our knowledge differential equations. In other words, it's another case where we're going to learn the math through the physics because that works, I think, better, rather than assuming that we know any math. But the mathematical name for this thing is a differential equation. So let me just write it quickly and then look in the chat. If there's things happening in the chat, bear with me for a second. But I do want to, there's something in the, I do want to pause on this. This is worth pausing on this differential equation. Again, I want to say, welcome to a differential equation. Not welcome to, this is the part where you were supposed to have taken a class on this already. This is the part where let's learn something together, okay? Something that's needed for physics. And you'll learn it better if you don't think that you were supposed to know something about it before. If you do happen to know, that's all great too. But don't think you need to have known something about this before we deal with it. But let me just, there's something happening in the chat. Pardon me. Oh yeah. Okay. This thing is an example of what's known as a differential equation. I have to be clear why it's called that. It's not just because there's a derivative in it. There's lots of equations in the world that have derivatives in them. They are not necessarily known as differential equations. There's something specific going on here that I'm going to explain. But also, just as a sidebar, this happens to be known as a second order differential equation for exactly the reason that you might guess or you might think, which is that the kind of derivative that it's involving is a second derivative. So just to be clear, let's say this were a fresh math class. Let's say a math class that existed in the year 2020 and therefore, or whatever. Let's say this were a math class and you were here to learn differential equations. What you would do, of course, is you'd first learn first order differential equations because that's what you were here to learn. And then you learn second order differential equations because that makes sense, right? But that doesn't mean necessarily that they were invented that way or figured out that way or anything like that. In fact, or that first ones are more important or even easier or anything. We're going to start our discovery of differential equations in the way that it happened in history, in that what nature is presenting to us here, the facts of the matter seem to be arranged in what I'm going to call a second order differential equation. And we as physicists want to see if we can figure out what to do with that. And that's why it's coming up first, and it's the first one that comes up in physics. It turns out there's a ton of differential equations in physics. It turns out that a lot of physics is about the study of differential equations. It turns out that even F net equals ma, when you really sit and think about it, since it's a statement about acceleration, which is the second derivative, F net equals ma, in fact, is a second order differential equation. A lot of nature is described by second order differential equations, and a lot of physics is spent trying to unpack them. Again, it's why we're a science, not a math class. We're studying things as they emerge to us in nature, not as we organize them in our brains. So we're going to look at this thing. So what makes it second order is that it happens to be a second derivative. But why is it even called a differential equation? Or like, what's interesting about this? Or why are we going to have to, like, what do we do with it? And I'm sorry. This is what, of course, the math methods homework was trying to get at from a different angle. Like the math methods homework, which most of you did, which is terrific. And I'm not talking about the vector part, like the main part at the beginning that so many of you did and did so well, is just asking you to like take derivatives and then play with them, and take derivatives and play with them. It's trying to show you what the nature of a differential equation is and how a differential equation actually involves like reverse engineering or thinking backwards. It involves fitting an answer to a question rather than the other way around in a way. So from one angle, that's what the math methods thing is trying to get you familiar with. I'm going to now try it from a slightly different angle right here. Like, again, we'll go over all that sheet. We will go over it in an organized fashion, but okay. I'm going to show you what I mean. This is all about, so it's emphasis, and this is the first time in my life, like I heard about variables, a dependent variable, independent variable, and I heard about the scientific method, like in 7th grade, we had to make posters and watch the plant, and like, did, the plant with more sunlight grow bigger or not? And we made graphs. Like I always knew about dependent variable and independent variable, but it never mattered. It all just seemed like a bunch of gobbledygook, like just irrelevant language to me until this point in my math education. We really want to distinguish between the dependent variable and the independent variable. The independent variable is generally the one that you plot on this axis. Generally, the dependent variable is on this, but really the key point is that the independent variable is the input and the dependent variable is the output, right? So here's what I'm saying. So a differential equation, well, the punchline of what I'm trying to say is that from here on in, we're going to call this thing a differential equation, and we're going to worry about it and have to do and think about it in sophisticated ways 100% because of the X on the right side. A big lesson that I'm about to try to show you all, but just so I don't play hide the ball, is if that X were a T, this is a heck of a lot easier to solve. In fact, so much easier that if that X were a T, like everything else were the same. Like, yeah, let me write this. What I'm ultimately want to show you right now, and even if I show you nothing else this class, it's worth it, and I probably will show you nothing else this class. If I'm writing this horribly. What I'm trying to say right here, I hope you write it more clearly than I am. The punchline that I'm actually about to like try to prove. So this is going to be another little sort of walk to the left kind of thing. But like if you got this far in your, what I really am, I guess trying to say is if you're doing your homework, right, and you got to question 9, I kind of am saying that you couldn't get this far. You can get this far. Maybe you didn't the first time. Maybe you didn't. But I think most of you have enough in your background, in your head, that even if you couldn't do this on your own, I think most of you can follow me that up until this point when I'm writing down makes sense, I think, from the physics and math that we know. Like to get to this point, I hope makes some kind of sense. Now, what to do at this point does require real thought. So much so that a lot of us who did more work after this point probably got that work from the web. And only we know in our hearts whether we understood what we wrote down from the web or not. But I want to say from here on, some thought occurs. And there's a reason for that, or thought is necessary. It doesn't mean it's impossible, but it's necessary. And the main reason I want to show everybody where thought now has to get involved in, like what to do with this expression, I mean, how to unpack it and get an X out of it. The thing you want to recognize right from the start is that it's this X on the right side that's actually doing something very interesting and unusual. If this X on the right side were a T, right, which is the other variable, right? So it could have been that like is an expression. If it were a T, then we'd have like 2 lines of work and we'd be done. It wouldn't be worth a whole class. It'd be a whole different beast if it were a T. But the fact that it's an X, in other words, the fact that we're presented with some derivative and we're told that the derivative is a function of the dependent variable, rather than being told that the derivative is a function of the independent variable, that's what makes this thing known as a differential equation. That's what makes this a hard homework problem. That's why it's totally fair if you get this far and then you honestly stop. You're like, I didn't know what to do from here. And then I know at least you're telling me the truth, like for real. Like it is very fair to not know what to do now. But reason number 1 that we don't know what to do now, whether we know it or not, is because there's an X sitting there rather than a T. Let me show you what I mean. Oh, sorry, I just lost. Let me show you what I mean. Okay, I'm going to present an exercise right now. It's new. It was not in the homework. It's to make a point about the homework. It's part of the curriculum, just so you know. It's not a sidebar. But it will mean it's going to take us even that longer to get to a full solution from the homework. I'm aware of that. you're not being assigned anything new for a little while. As like, just know that I know math methods is what's on the docket now. Any further homework that's new will not be assigned for a while until we catch up with ourselves. But I need to show you this so you can really appreciate what's going on with question 9. So I'm writing a problem now. That's like a do now for everybody. And again, this is, I don't know why I feel like I need to say this, but this is not like a tangent. I mean, this is like the point, the curriculum, but it's for you to keep you alive. Okay, I'm going to ask everybody now. I know there's like 18 minutes left. I do this every semester. This is a worthwhile exercise, even if it feels, this is like a math thing I'm going to ask you all to do. And it will get us to understand the math here. But wow, that was really fast. Wow. Okay, totally. I'm still going to ask everybody to do it. That's cool. But that's awesome. Even and put your answers in the chat as you get it. But I do want everybody, like, even if you see an answer in the chat, I want everybody to make sure that they know how to do this before I go any further. And again, I can take a million correct answers in the chat and you can all submit it for the class participation points. And it's great that some people are very fast with this, but some people are less so. So everybody take a moment on your own piece of paper to figure this out and translate. Like I'm asking you on purpose, a simpler version of what we have in front of us. And I'm on purpose making it a first derivative, not a second. So it's not supposed to be a trick, but I'm saying, imagine that you're given this, and also imagine that you're given this extra piece of information just to make things clear. Then find what X is. Okay, so I'm just going to put now, and I've gotten one good answer in the chat. I'm still going to pause to let everybody think about it for a second, which is awesome. And I'm not, and by the way, I was impressed that the answer came in the chat so fast, but I'm not necessarily even saying it's right. I mean, it looks good, but it could be wrong or whatever. So I would like everybody to just think for a second. And if nothing else, just even if you don't want to share your answers, which you don't have to, if you guys could put a thumbs up or just some indication in the chat or something, like once you've actually thought about it and gotten an answer. I won't call on you if you don't, but just let me know once you have an answer to this. Oh, I keep changing the view. Okay, so it's 117. So now some things have happened in the chat. So I've gotten some things from people in the chat, private and public. I've gotten some answers and good answers, and the answers are good. And I'm going to pause for, but again, I do want to emphasize to anybody, in both directions, it's not a race. Like it's not a race. It's not a race to be slower. Like in other words, I want everybody to take whatever time they can for a minute. And it's absolutely kudos to, like, nobody should, even if they think a right answer is already in the chat, shouldn't stop. That should, everybody knows in their heart whether they're thinking this through or not. And often for many of us, seeing a right answer or knowing there's a right answer there to check your work is only all the more helpful. Like it doesn't have to stop. Having a right answer sitting somewhere accessible, just like odd exercises in the back of a textbook, don't at all have to stop anybody from thinking, right? I mean, I'm talking to everybody now. Everybody should take whatever time I actually give them to think. And it's first and foremost always the professor's problem, who professors by nature are people that can't deal with silence. Like they talk their way through all thoughts. So professors never give everybody enough time to think. So I've gotten just enough answers to know that some people are totally on top of this. I want to just give another moment for anybody to think, but I will say, if you've already gotten an answer also, and we're not going to go too much farther than this today, but if you have gotten an answer where you might see where I'm going with this is, well, no, actually, I'm just going to talk to everybody now. I have gotten some answers. I like, and I'm getting more as I'm talking, which is great. Wait a second. And I can't even see it. Awesome. Yes. Oh, I'm getting a lot now. Okay. Oh, sweet. Okay. All right. This is a lot. So I think I will start talking about it, but this is great. I definitely see that people are, and again, please, good. A lot is coming in now. Right. And again, for each one of you, I hope you understand, like this is any assignment portal that with points that seems like it applies to this moment where you're putting in an answer in the chat right now. I mean, I could think of at least 3, right? You've participated, you've taken a risk on writing something that could be right or wrong. And I think there's at least one more. You all should and each one of you realize this too. Say you're about to put something in the chat and then you're like, well, 4 people have already put it in. What's the point? Well, think about it this way. You know how much happier I am when 5 people put something in the chat than 4 or set, like each person that adds to the chat does make it seem like more people are participating in this class. It does make it a better class. So don't think your answers are redundant just because like someone else put those answers in. It doesn't make them right or wrong or redundant. That said, why am I saying all this? Because I'm psyched what's happening in the chat for one thing. And I think these answers are right. There was another reason I was saying this, but okay, right. And that's right. I agree with all the answers. Hey, there you go. Right. Right. Okay. So this is good. So I think people are seeing what's going on. I'm going to quickly go over this. I'm not going to ask you to. I think a lot of people have gotten it. I'm going to go over it slowly, but I want to show you, but always, like always in physics, if you got the right answer, all the better reason to then pay attention to what I'm going to do. Because what I want to show you is the steps that you did, whether you knew it or not. And there's one step at least I'm going to stick in there that might not have been in your conscious brain, just like sort of I was trying to do with question number 4 on the homework. I want to show you the steps that are actually happening to get a right answer to this, because then those are the steps that you would have to do when we put an X in instead of a T. Like this thing that I'm about to do right here, this thing that I'm about to solve. To be clear, I'm not saying it's easy peasy or a joke or anything, but what it is that we're about to solve here is not a differential equation. This here is an example of an equation that has a derivative in it, and that's not giving us the information we want. Like this looks a heck of a lot like what we have in question 9. We want X as a function of T. We want space as a function of time. We are physicists. But all we have is some information about the spatial derivative, right? So it looks just as annoying as question 9 did in the homework. We want a function, but we unfortunately only have its derivative. The thing about this one is the derivative is being expressed as a function of the independent variable of T, and therefore it doesn't actually require any special methods to unpack. Like what we do here, I'm going to do it now, and I'm going to stick in at least one step that some of you probably didn't do. Please write this down. Like even if you got this right, see the one step that I'm sticking in for future reference. I'm saying, okay, but I'm going to solve it. I'm looking for X as a function of T using these 2 pieces of information. The first piece, okay, just so I was given this, right? I wasn't told x is a function of t. I was told what the derivative of x with respect to t is as a function of t. What do? Strictly speaking, the very first thing I do is I multiply both sides by dt. I know many of you are thinking, oh, take an integral or something like that. And you're right. But strictly speaking, I cannot integrate. There's nothing about this expression that can be integrated. I can't take the integral of the left side because I've never seen a full derivative in an integral. And I can't take the integral of the right side because there's no d anything on that right side. What I can do, and I know both this seems maybe unnecessary to some of you, and maybe it even seems illegal to some of you, but what I first do is do this. I multiply both sides by dt because I actually can, because a derivative is just a ratio of differentials. It is a ratio, and ratios often work this way. I multiply both sides by t, and then I can go like this. I'm being extra careful as usual because I think this extra care is going to be required when things get a little more funky. But strictly speaking, in other words, if you thought, oh, I mean, any of you who thought, oh, Yaverbaum gave us a derivative, but we really want the function. So we got to sort of like do derivatives backwards. So we do integrals. Of course, you're right. I mean, an integral, it turns out, is the inverse function of a derivative. That's wonderful. It is the best. But you still have to be careful about how you do integrals. Anybody in a math class who's ever seen an integral always has not just that symbol, but the d something in it. And I know a lot of us never really knew why that thing was there or what, but you do know that whatever follows after the d in an integral is the variable of integration, right? Like that's what tells you what to treat as a variable and everything else you treat as constant. And there's more going on than like to integrate is to add up an infinite number of infinitely small things. The integral sign tells you to add. The things that you're adding are the infinitely small things. If you don't have a d something, then you're not integrating anything. Anyway, so I multiply both sides by dt so that both sides are now integrable. And I am now going to integrate both sides. Notice, and I'm being careful, no one said, it doesn't look like anybody said anything to me about the boundaries of this integral. It doesn't look like I don't know offhand what they are. So it looks like what I just have here is an indefinite integral, and indeed I do on both sides. So I'm going to treat it that way. I'm going to be careful. I'm going to say on the left side, the indefinite integral dx is like x plus c, right? Strictly speaking, right? And then the right side, well, I can, if you want, I can go one more step. We can take the constant out of the integral. So now we have this, right? I'm just being extra careful. So then the right side is something like 5t, like now I'm integrating. But again, it's an indefinite integral. So technically it's plus also some c, but not the same c necessarily as on the left side. So I better call it something else. Maybe I'll call it c2. And I'll call this one. Now I'm being very technical, but do we agree with this? So does everybody, sorry, let me just look in the chat. What's happening? Okay. Right. Is everybody, and again, this is, I'm sure, like, I know from the chat that a lot of you got 5t squared over 2. Now I'm being like a picky teacher worrying about the constants, but I was being picky when I multiplied both sides by dt, but I have to be that picky because otherwise I really have no legal right to integrate anything. So now I have this. Now I'm going to do one trick. Like technically speaking, I've got to keep track of these constants because it's an indefinite integral, and technically it's a different constant for each side, but it is just a constant, right? Like C1 stands for some number that I don't know what it is. And C2 stands for some other number that I don't know what it is. So of course, so let me just recopy this. So what we have so far is this. I forgot what I forgot. Wait. Oh yeah. So we have this so far, right? Well, that's a lot of unknown constants. I mean, if I'm trying to get an answer here, like how am I, but one thing I can say is it's going to seem like a trick, but it becomes a very handy trick. I'm going to just define a new constant called C3 to be defined as the, oh, and I see it's 127. We're just about there. C3 is the difference between C1 and C2. Why would I do that? Because then I can say like, I can subtract C2 from both sides. And this all seems like, and then I can just say, oh, okay. Like, in other words, if I don't know what C1 is and I don't know what C2 is, I'll just make up a name for the difference between the two of them, call that my arbitrary constant. And in fact, once I call that C3, it's the only constant in town. So then there's no reason to call it C3 anymore. I'll just call it C. So now I have this, so I'm almost there. Or even better, I'm almost there. And I can even say this. Now I could say minus C from both sides, but I never said whether C was positive or negative anyway. So I might as well just say this. So now we're just about there. The only thing is we don't know what C is. And this is where we're going to stop today. I'm not going to do the other one, but I'll submit to you that if I gave you the exact same problem, but I changed the T to an X, then it's a different answer. And that's where we're going to pick up next class. But just to finish this off, and I know you guys know this, but I'm saying this just so we can be complete, because I know class is about to end. The way to get C is to look at the one other piece of information that I was given in the problem. I was also told something about the value of X when T equals 0. Just like in the thing on the spring, you're not just told that you have a spring, but you're told what the initial position of the mass is, right? There's always that initial condition. So we recall that X of 0 was defined to be, I think, 7 or something. I don't remember what I said. I think it was 7, just checking. Yeah, 7. And this is what we're going to, so what does that mean? It means that when T is 0, X is 7. So it means 7 equals 5. Like, it means that when you plug in 0 for T, then you apparently get 7. So it means that 7 equals 0 plus C. And this is where we're going to end. 7 equals 0, right? That's what that means. Therefore, 7 is C. And so what's the point of that? So the expression that we got. Now, I know some of you got this a lot faster, but I'm just showing you all the steps that were technically required so we can do the other one. So what we ended up getting was, and that was the answer that I saw in the chat. That was very impressive. And it's right. I guess I'm going to leave you, but now try, not now, but like, right when we pick up, I'm not giving you more new homework, but where we're going to pick up right from this next class is, what if instead I had given you that dx over dt is not equal to 5t, but if instead I had said is equal to 5x, and if I had said and assume that x at value 0, and there's a reason I have to do this, you'll see when if I instead of giving you as 7, if I give it to you as 1, I don't really have to do, but let's see, then try the problem and you'll see you do the same method, but you'll get a very different kind of answer. And we'll just leave it there for now. Like, that's class for now. I mean, I'm going to so I'm saying goodbye. If you guys are good, just if you don't mind, just like unmute for a second and just say goodbye or put goodbye in the chat or whatever. And thank you, but I'll hang out for a second if anybody has any questions or whatnot. And I'll post this obviously, but I'm good.
Good afternoon.
You too. Thank you. You too. Awesome.
Have a good afternoon. Bye.
Thank you very much. Thank you, guys. Thank you. Awesome. Thank you.
Bye, Professor. Have a good afternoon.
You too. Thank you very much. Thank you.
Bye.
Bye. Thank you very much. Awesome. All right. Awesome. 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 Thank you. You guys are good. All good. You guys good? Ellie, Nelly, and Heaven, you guys are good? Or and you're good, Heaven? Or